Yeah.
All right, let's go ahead and get started. A little disclaimer here to start the class. I feel terrible today. Thought of canceling class, but we would regret that later when we're trying to make up for it. So I'm going to try and get through this, okay? So pay attention to mistakes, simple mistakes. If something is obviously not done right, just stop me.
Professor, you need that 1 + 1 is not 5? Darn it.
It depends. All right, so today is all about 4.1, which the main point of this section is to use what's called the closed interval method for finding the absolute maximum and minimum values of a continuous function on a closed interval. Now, I'll use the word absolute maximum and absolute minimum. I'll use that terminology. I might replace the word absolute with global, all right? So if you hear me say global max, global min, it's the same as absolute max, absolute min. And we talked about that last class, right? The idea of an absolute max and an absolute minimum. So this method is used universally as the way to find the highest and lowest points on a graph as long as this function is continuous on a closed interval. And the method is pretty straightforward. We have to take the derivative because we have to find the critical numbers. That means taking the derivative and setting it equal to 0, and also looking at the derivative and discussing any points at which it may be undefined. And that would be at points where the derivative doesn't exist. All right? Once we find all the values where that happens, we just take those numbers and we plug them into the original function, and we also plug the endpoints into the original function. The biggest value that comes out is our absolute maximum. The smallest that comes out is our absolute minimum. All right? So what I wanted to do today is start working through some examples. All right? And on the homework solution videos for this section, I did all the odds. All the odd problems out of the homework set you have. So I figured in class I would do some of the evens. And that way you have a good mixture of problems. All right, so I'm going to start with, this will be a warm-up problem, okay? 38, which is f of x equals 5 plus 54x minus 2x cubed. And we have the interval 0, 4. So the instructions here, as stated in the book, are to find the absolute maximum and minimum values of f on the given interval. So this is perfect for closed interval method, right? We have a function. Is it continuous? Because we need that. Those are the big conditions we need. Or that it's continuous on a closed interval.
It should be a polynomial.
Yes, it's continuous because it's a polynomial function. And all polynomial functions are continuous everywhere. This goes back to when we talked about continuity. There was a note in the notes that I provide for you that said all polynomial functions are continuous everywhere. All rational functions are continuous on their implied domains. All trig equations or trig functions are continuous on their implied domains. Now we'll talk more about that as we proceed with more functions. You going to relocate, or is that chair broken? It's messed up. Y'all can move. You're all right there. You're okay. Okay. All right. So we have a continuous function on a closed interval. So we proceed. First thing I'm going to do, find the critical numbers. So there are two things I need to do. Figure out where the derivative is 0. And the other thing I need to do is take a look at the derivative and ask myself, does the derivative ever not exist? Is it ever undefined? All right, those are two things. So the derivative of this, I said this is a warm-up problem because the derivative of this function's pretty easy, right? Very easy, hopefully? Yes? Okay. So the derivative of this function is, you know what, and I like to do the derivative somewhere else so I can just have it as a reference. Let me do the derivative right here. What is the derivative?
-6x.
Okay, so yeah, you can write it whichever order you want. 54 minus 6x squared, or you could write negative 6x squared plus 54. So there's our derivative, right? I need to set it equal to 0. And that's just a little quadratic equation. And to do this one, what would you do?
Factor out of 6.
You would factor out a 6, that's fine with me. And what would that be? 9 minus x squared, if you factor out a 6.
I can factor out -6.
You would have factored out negative 6?
But then I can separate it again.
Yeah.
Yeah.
Because then you get a difference of 2
Yeah.
squared.
Yeah.
So look, at this point right here, this quadratic equation, the way you solve it is really up to you. I would expect that everyone can solve a quadratic equation. I'm just following what people said, and yes, I agree with this, and you may do it a little different, that's fine.
Well, I didn't see it until after I took out the 6.
So what, if you were with this right now, what would you do?
Factor out a negative.
You would now do a negative?
Yeah.
Well, no, because then you'll have some.
Factor out the negative and then make off, and then that's a difference of 2 squares then on the inside.
Well, this is a difference of squares also.
Yeah, you can factor that in.
You can do different squares without having to factor out a negative. That's still a difference of squares. It's something squared minus something squared. So you can still do this, right? That's fair? And now you set each factor to 0. So you set 6 equal to 0, which will never happen, right? Set that to 0, that to 0. So we get 2 answers, don't we? 3 and negative 3? Those are 2 of our critical numbers, or so far 2 critical numbers. Now either now or later, it depends on you, you need to make sure that these critical numbers lie inside the interval. So do both of these lie inside this interval?
No.
Not both of them, right? Negative 3 doesn't. So what do we do with it?
Throw it out.
We're just going to throw it out. Okay, we're gonna chunk it. All right, we're going to get rid of that because it's not in the interval. The danger is if you don't remember to do that, then later on when you go plug these in, step 2, if this turns out to be the biggest number and you say that's your answer, well, that wasn't even in the interval. You know, like you weren't looking in that window of the function. You were looking outside. So make sure you do that at some point. All right, we also have to look at where the derivative does not exist or where it's undefined. All this means is look at the derivative and see if there are any domain restrictions, any domain problems. Well, it's a polynomial also, right? So it by itself is continuous. It's well defined. There's no value of x I could ever plug in that's going to cause a problem here. So this wouldn't apply, right? So you could, say whatever. I'm just going to cross it out. All right, so I actually only have one critical number, don't I? Right? One critical number. So I move on to step 2. I think the book does this in 3 steps, but it's really just 2 steps. What am I going to do now? Plug the critical number into the original function, plug the endpoints into the original function, and compare them. Right? So it doesn't matter what order you do this in. I'm going to take my original function, and I'm going to plug in. You can do them in order if you want, but again, it doesn't matter. Where are my good markers? You don't care which order I do, right? So we had 3, right? We had 0. We have 4. Those go into the original function. I'll do the 0, because that's easy, right? And those are getting plugged into the original function, right? Do not confuse yourself. Don't plug them into this. Now you may be saying, well, I know, because you said this, like obviously don't plug it into that. But later on, we're going to be doing a different method when we move into the, do you remember I told you that we're going to focus on a closed interval first, and then after that we're going to let it just keep going. The function will just be allowed to open up. When we do this method, we're actually going to be finding numbers and plugging them into this. And so we don't want to confuse ourselves. With closed interval method, our numbers that we get always go into the original function. All right. Did y'all get these? I was just talking while you were doing that computation for me.
149 and 189.
149 here?
Yeah.
And 189 down here? Anyone else confirm or?
I got 113 for 3.
You got 113 for 3?
Twice plugged it in.
Maybe I didn't do a calculation. Maybe my cube is wrong.
Do I need to break out my calculator? What do you got? You got 113? 113 for the first one? You got 93? Oh, shit. Okay, I better do it. 5 plus 54 times 3. Minus 2.
Oh, okay.
113 for the first one. That's correct.
Yeah.
Oh, for 4 you got what? 93?
They're right.
93? Okay, okay.
I put it squared instead of the cube. Sorry.
No problem. 93.
I was like, how can we do that?
So this is obviously going to be our global max, right? And this one right here will be our global min. And I said last class that I also like for you to write these as points, like an x and y coordinate. Why did I say I like for you to write them as points? Because I said so. Easier to find what? Like, instead of just telling me, hey, the global max is 113, the global minimum is 5. By writing it as points, there's additional information here, isn't there? It's telling me where it's happening, right? If x is 3, that's where I get the maximum to come out. If x is 0, that's where I get the minimum to come out, all right? Now, I'm not going to graph this one. If I went to my computer and graphed it, I would cut it off at 0 and at 4, and then this would be the highest point and this would be the lowest point, okay? We'll graph some of the more complicated ones. All right, moving along. That was number 38 straight out of the book. I'm going to skip 40 because 40 is another polynomial. And the polynomials are just too straightforward. So let's do something more complicated. Here we go, 42. This is f of x equals x squared. This is in parentheses, x squared minus 1 cubed. And this is on the interval -1, 2. Now that is still a polynomial function. If I were to expand that out, multiply x squared minus 1 times x squared minus 1 times x squared minus 1, do all the multiplications, it would be a polynomial. But I'm not going to do that, right? I'm just going to leave it like this. So we first check, do we have a continuous function on a closed interval? Yes. All right, so we're going to apply the test, or the method. I'm going to need the derivative, so let's go ahead and get the derivative now. And to get this derivative, I will use chain rule, right? Chain rule. So first thing happens is the 3 comes out, and then it's everything that was there, now to the second power, because I reduced the power by 1. And then chain rule says times the derivative of what's inside, which is just 2x. So this turns out to be, if I clean this up a little bit, pop that 2x out front with the 3, it's going to be 6x. And then x squared minus 1 squared. There's my derivative. Right? All right, so now step 1, find the critical numbers. I'm going to set the derivative equal to 0. That's one thing I'm going to do. Then over here, I'm going to look at where the derivative doesn't exist. So setting this equal to 0, I'll do it right here. Fortunately for us, it's already factored, isn't it? This is already factored. Like there's multiplication in here. So I can just set each of the factors equal to 0.
It's a different squares.
and then I'll have a difference of squares. So I can set 6x equal to 0. That's one equation I'm trying to solve. Then I can do x squared minus 1, that entire thing squared, right? Squared. So I could put the squared here. I could also write it twice. Doesn't matter how I do it. These are going to break down to be the same thing, aren't they? Difference of squares here, difference of squares here. I'm not saying this is the only way you could do this. I'm just showing you a particular way you could. This gives us, when I set each of these 4 factors to 0, 2 of them are duplicates, right? So I'm only going to get 2 answers from this. 1 and negative 1. And then on this one, don't forget this one, x is 0. Divide both sides by 6. So we have 3 potential critical numbers. Would you like to check now to see if they're inside the interval? Check. Okay, 0, is it in there? Yep. 1? Yep. Negative 1? It's an endpoint also, right? That's okay. Just leave it there. You're going to have to plug the endpoint in anyway. So when we plug it in, we're not going to plug it in twice. We're only going to plug it in one time. And then I need to check to see if the derivative ever doesn't exist. So when we look at this derivative, are there any numbers you could ever plug in for x that would cause a problem? No. It's polynomial again, right? So we're good? This is we're going to have this happen eventually. We're going to have something to look at. Just not yet. So now I'm going to write down step 2, which is to evaluate my function at all of my critical numbers and the endpoints. So let me get these. I have f of 0, f of 1, f of negative 1. Those are my critical numbers. And then I need the 2 endpoints, negative 1, which I already have up there, and 2. Go ahead and break your calculators out if you need them and figure those out. And while you're figuring those out, I'm going to graph this and see if we get the correct answer. Something doesn't look right there. Trying to figure out why it graphed past 2 there. Was it? Pardon? No, that's just my viewing window. Let me apply this. Let me close up. Maybe that's causing a problem. Huh. That's really weird. Whoa. Okay, that's better.
Yeah, that's what I have.
I have no idea why that did that. So there's our graph. And at 0, you got negative 1. How about at 1? You got 0. And negative 1, you got 0 also, right?
Yes.
Negative 1 squared is 1. Minus 1, you get 0 again. And then how about at 2?
27.
27. So we have our, right here, I can write this as a point, 227. The global maximum is 27, right? It occurs at an x value of 2. The global minimum is what? -1, but it occurs at 0. So you can see here from our graph, this is the lowest point, right? And the highest point's over here. So the mathematics matches up with the picture, right? That's a good thing. Are there any questions on that?
Professor,
Yes.
say for instance the graph instead of that being a -1 becomes a function that went to 1, so we had 2 zeros. Would that just be that endpoint would be the global minimum?
What are you saying?
I was just saying, let's say for instance if that -1 wasn't there, for this one right there, that answer right there, let's just say that was some other number. And yeah, right, and we have now 2 small ones.
Okay, that's a good question. What would the global minimum be here if that was what we had? What would the global minimum be? 0, okay? It would happen at 2 different points, but the minimum is 0.
We would put it at both points.
What you could do is you could say, you could say global minimum is 0, or you could write the 2 points. This is the point 1, 0, and -1, 0, right? And this would imply that the minimum value is 0, and that it occurs at 2 different places. All right, let's do another one. Starting to get fun, huh? I'm starting to feel better. I felt like crap. I start doing some math. I feel good. It's a good thing. All right.
Which number is it?
This is 44. Okay. Rational function, right? Rational function. Is this a continuous function on this closed interval? Well, maybe. You have a problem here that you have to consider. Could the denominator be 0? Maybe, right? And what if this denominator, this is a big what if, but what if I plug in 1 and I get 0 down here? Then 1 is in here, right? And that would mean this is not continuous on this closed interval. And so we couldn't use the method. So we have to first check, is that a continuous function on that closed interval? So let's just talk about the domain of this function. What is the domain of f? Well, what can we not have happen? What are we trying to avoid? 0 in the denominator, right? So let's just do some work over here. This is like scratch work. Let's see if we can solve this equation. Is that ever 0? I'm asking myself, is that ever 0? And if it is, then does it happen in here? Because if it does, it's a problem. Understand that? All right, so you get to solve that. It's not going to factor. Okay, you can't factor that quadratic. It just doesn't work. So your only option is a quadratic formula, right? So x is equal to, the quadratic formula is something like -b plus or minus square root b squared minus 4ac all over 2a, all that thing, right? So you've got that somewhere, right? So I'm going to put it in here. -b for us would be -1, right? Because b is -1, so we take the opposite of that, 1, plus or minus the square root of b squared, 1, right? Minus 4 times a, which is 1, times c, which is 1, all over 2 times a, which is 1. You all know what I'm using here, right? Okay. Immediately, I see there's a problem. Y'all see it? This is going to be 4 times 1 times 1 is 4. 1 minus 4 is -3. The root of a negative number is an imaginary number. And we are not allowed to use imaginary numbers in this class, right? It's off the table. So that means that there is not a real solution. A real number solution does not exist.
Because it's a complex
because it's a complex number. So there's no number here or anywhere on the number line that's going to make this thing 0. It's an imaginary number, right? That means that the domain of this is what? Everything, right? Domain of this function is anything. I can plug any x I want, any number I want. As long as it's a real number, I can plug any number I want in to this, and I don't have any issues. Okay? So now I can ask myself the question again. Is this a continuous function on this closed interval? Yes, because it's a continuous function on the entire number line. So it's going to definitely be continuous on that. So this is back in when we were talking about continuity. I said that a rational function is continuous on its implied domain. Well, here's the domain of the function. It's everything. So this is continuous everywhere. Got it? Okay. So now we can proceed. I'm going to need the derivative, right? So may as well write this down. It's going to require some quotient rule. Derivative of the top, 1, right, times the bottom, plus, minus, times, what is it, minus, right? Minus what?
Derivative of the bottom.
Derivative of the bottom, which is 2x minus 1, like that? Like that? I need parentheses around the derivative of the bottom, right? Times the top, x, all over the bottom squared. There we go. Now that was the raw derivative, right? Before. I need to actually clean this up now. And the reason I need to clean it up is because I'm going to have to set it equal to 0. And so I need it to be as nice looking as possible. So let me continue. I'm not going to do my closed interval method yet until I get a prettier version of this. The 1 doesn't really need to be there, right? I can just distribute the 1 through. I can distribute the x through here and the negative through also, right? So what would that be? Minus 2x squared plus x. All over x squared minus x plus 1, that quantity squared. Clean up that numerator. See if any of these markers are good. No. What's the new numerator?
Negative x squared plus 1.
Negative x squared plus 1?
Which is the sum of squares.
Negative x squared plus 1? Is that what you said?
Yeah.
Negative x squared plus 1. I could write that as 1 minus x squared, right? That's the same thing? Negative x squared plus 1? Doesn't matter. You could do it either way. And then the denominator? X squared minus x plus 1 squared. All right, that's pretty clean, don't you think? That's a pretty clean derivative. I don't see anything else I could really do. Okay? So that's our derivative. We'll just leave it like that. And now let's go through the process of the steps. So the first thing I'm going to do for the steps is figure out where the derivative is 0. So I take my derivative, right? 1 minus x squared over x squared minus x plus 1, that quantity squared, and I set it equal to 0. Does that look bad to you? I mean, does that look like an equation you feel like solving? Does it look intimidating a little bit?
Yeah, need some algebra, but it's not easy.
What sort of algebra are you going to use to solve that? I'm going to leave that right there. All right, so time out. Time out. Let's talk about something. That's a terrible marker. What if I have a fraction? Just as bad. What if I have a fraction equal to 0? The denominator doesn't matter. Anytime a fraction is equal to 0, all you have to do is look at when the top is 0. Why?
Because the bottom will make it undefined.
Yes. Well, the bottom could be undefined, which would be a problem. We actually have to consider that. But let's say someone gave you a fraction, and they said, solve this thing, right? Couldn't you always just multiply both sides by b? And if you did that, what would you get on the left side? Left side, you get what? The b's would cancel, you get a. And on the right side, 0 times b would be 0. So if you ever have a fraction that's equal to 0, you can always just convert it into setting the numerator equal to 0. Do y'all understand that? That's super, super good shortcut for us here. That fraction, although it looks complicated, really just turns into what? 1 minus x squared equals 0. I just look at the top being equal to 0. And now we're in a pretty nice place, right? I know some of you would say the left side is difference of squares, and you could do that. I'm going to do this one a slightly different way. If I were doing this, I would just move the negative x squared to the right side to make it positive x squared. And then I'd take the square root on both sides. And I have to do plus or minus. I have to do plus or minus because I initiated the root.
But then one of those answers is going to fall within the...
Is it not? Yeah, it's going to be outside. But let me write down what we have here. Square root of 1 is 1. So we get x is 1 and x is negative 1, right? Those are our two potential critical numbers so far. And you're noticing that negative 1 doesn't live in here. So let's chunk it. What I've always found kind of cool about this is that this process of setting the derivative equal to 0 and getting the critical numbers, the derivative has no idea that we've cut this thing off at 0 and 3, does it? It has no clue. So if this interval would have been opened up, let's say between negative 3 and 3, then this would be in here, right? So the derivative does not care what your interval is. It's going to give you all the critical numbers for the entire domain. All right, so now, are we done? Can we plug in and evaluate now? I have to finish up the critical numbers. I need to also look at where's the derivative not exist. Oh, I almost erased it. There it is. I needed this. There's our derivative, right? Yeah. Where's this undefined? Potentially when the denominator is 0, right? If this denominator was 0, we'd be in trouble. But we already know that quadratic doesn't have a real solution. So we know that this denominator can never be 0, so that's not going to apply. Eventually, a problem that we do, we're going to have something here, okay? Any questions? All right, now we can go to step 2, right? Plug in. Plugging in. Critical number is 1. Endpoints, 0 and 3. You plug, I graph. That was it, right? Okay. 0, 3. All right, for 1, what did you get? 1? For 0? 0, and for 3? 3 over 7? 3 sevenths?
Oh, right, sorry.
So here we have at 1, 1, this is our max, right? I'll say abs max instead of global max because I want you to see both terminologies used. That's our absolute max. The absolute max of this function is what? 1, right? That's the absolute max on this closed interval. The absolute minimum, 0. And they occur, as you can see, here at 0, 0, and then here up at 1, 1. Questions? All right, so do you understand the method? You get the idea here? The only thing that's going to change now is that the functions are going to get more complicated. And each problem could present its own sort of algebra that's required. So let's see what the next one is. Oh, this one looks fun. (46). They use the variable t, so how about I use t also? F of t is t plus cotangent of 1/2 t. And the interval that they're giving you is the interval pi over 4 to 7 pi over 4. Ah, now we got some trig stuff in here. Now, in a pre-cal class, you might be asked to graph cotangent of 1/2 t. That might have been something that was fair game in pre-cal. Here, we actually added plus t to it. That's something you would not graph in pre-cal. And what we're doing in this class right now is we're not trying to graph this. We're just trying to figure out its highest and lowest points on that closed interval. In a couple of sections from now, we will be able to graph this. All right? So we've kind of opened up Pandora's box of functions now. There's really nothing that's off the table anymore about in terms of what we can try and find the max and min of. As long as we can take the derivative of it, set it equal to 0 and solve it, this will work. All right? All right, so let's start with this derivative. The derivative of this function, f prime of t, is 1. All right, that's good. 1 plus, is it plus? It's going to be minus, right? Because the derivative of cotangent something is negative cosecant squared of the something. Yeah? Good. Times the derivative of what's inside of that, which would be 1/2. Everyone agree with that? Not a whole lot I can do to simplify that or clean it up. I could just write maybe this. 1 minus 1/2 cosecant squared of 1/2 t. I just moved the 1/2 out here in front. Is that okay? There's, oh, you know what? What did I forget in the very beginning? Hit me with this. No, I'm kidding. What did I forget in the very beginning? Is it a continuous function on that closed interval? Got to check. Maybe we'll get lucky and it won't be, and then we can just move on to the next problem. So is this continuous here? Well, what do we need to concern ourselves with? Is that ever going to be a problem? No. Cotangent, on the other hand, could. Maybe. Let's see. What is cotangent? I'm going to write this down here. Right now I'm looking into the domain of f right now. I'm kind of thinking through this. Sorry, I got ahead of myself there. Domain of this, well, let's look at cotangent. Cotangent of 1/2 t is the same as, let's switch it to sine and cosine instead. It would be what over what? It would be cosine over sine. So this is cosine of 1/2 t over sine of 1/2 t. Y'all agree? That's what that is? Now, if you look at it this way, then this piece right here could possibly be undefined. And it's going to happen when potentially this piece is 0, right? And now I need to actually think about that. Could that be 0? Sine function, it's a sine curve, right? That's 0 a lot, right? It oscillates back and forth. So let's continue this thought right here. I'm asking myself from here, when is sine of 1/2 t equal to 0? Where does that happen? At t is 0, yes, I agree. So look, if I plug pi in there, yeah, so look, everyone here took pre-cal, right? I always tell my pre-cal students that there are 2 major concepts that you have to know when you come out of pre-cal. You have to understand the unit circle, and you have to know how to solve trig equations. This is a trig equation, and I want to go through right now and make sure everyone knows how to solve this. Because if you can't solve this, you're not going to be able to do a lot of the problems here. Anything that involves trig stuff, you'll be stuck. And I think this is what we referred to, last class we were talking about, like general solutions. This is what I'm talking about here, okay? So let's just take a step back, make sure we know where we are in the problem. We were making sure that this was a continuous function on this interval. To do that, we had to look at the function. We realized cotangent could have a problem. There's where it could happen. I need to know when that happens. Once I figure out where this happens, I want to see if any of those answers are in here, right? Okay. The derivative is just going to have to wait. So now I'm going to try and solve this. The way that I show my pre-cal students to solve this is to say, look, this is sine of this, right? Forget that. That's an angle, right? Everyone agree that's some angle? And sine, if we go to the unit circle, is always the y-coordinate of the point that you're on, right? Sine is the y-coordinate. So where's the y-coordinate 0 on the unit circle? At 0 and at pi, right? 0 and pi. But it could also be, this is 0, right? That's pi. But we could also have all the way around, which would be 2 pi, or you could have all the way around and then one more half rotation, which would be 3 pi, or 4 pi, or 5 pi, or 6 pi. There's an infinite number of angles where that could be 0, right? So I need a general answer that includes 0, pi, 2 pi, 3 pi, 4 pi, right? All of them. And you could also have negative answers. You could have 0, and then a rotation clockwise instead of counterclockwise is called a negative angle. We could have negative pi, negative 2 pi, negative 3 pi, right? So to get that, again, what I tell my pre-cal students is to pick one of these. So let's pick this one right here. That's the angle 0, right? What does it take to get across over to this other one? Pi, and then to get back to this one? Add a pi again. So what I'm doing is I'm saying this is 0, right, plus any multiple of pi. I could have 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, or negatives. Negative 1, negative 2, negative 3. So how do I represent all multiples? We use either k or n. So what do you all remember from pre-cal? K or n? K? K? Anyone know n? No? I don't know why. N is what I usually use, but I'll use k. So k pi. 0 plus k pi. Where k is what? K is equal to what? Any integer. So this gives me an infinite number of answers. It is understood by writing this notation that the k is an integer. So if I let k be 0 right now, then my answer is what? If k is 0, I get 0, and that's an answer, right? If I let k be 1, pi, and that's an answer, right? Question?
Would it be pi to 1/2? You have to tag on 1/2.
Okay, so look, I'm not even considering this yet. Okay, follow me so far? So far we're okay? Everyone's okay with this formula? And the 0 didn't matter. I could have written just k pi, right? Because 0 plus k pi is still k pi. All right. So when I was over here, I was saying to myself, hey, look, when is sine of something 0? When could that happen? Well, it happens whenever this something right here, right? When this something is equal to that. If this in here is equal to k pi, then I'm going to get 0. So my next step is to take the inside, the argument of the trig function, take the argument of the trig function, 1/2 t, and set it equal to our general solution here, k pi. And then finally, solve for t. So if I solve this for t, I can multiply both sides by 2, right? And you get t is what? 2k pi. There you go. So sine of this junk in here is going to be equal to 0 if I ever plug in for t 2 pi k. So can someone just list off for me right now the t's that would cause a major problem with this function? Give me one of them. If t is what? 2 pi, is that what you're talking? 2 pi? That's you just plugging 1 in for k, right? 2 pi. How about if we plug in 0 for k? 0, right? We could also have 2 pi. We could also have 4 pi or 6 pi. But then you could have also had all of these negative. So it could be like plus or minus, plus or minus, plus or minus. Understand? This is your general solution answer. All right, back here. What's the domain of f then? What's the domain of f? Everything except that, right? Everything except these t's. You are not allowed to plug these t's in. If you plug these t's in, that sine thing is going to be 0. Sine was the denominator on this cotangent when we rewrote it, and that would have given us division by 0. So how do I say the domain of f is everything except this? Yeah, just put this. As long as t is not equal to 2 pi k, we're in business. And I changed the order. I put 2 pi k instead of 2k pi, but that's okay because it's multiplication. Okay, can anyone tell me what I should do now? I've done all this work. Before that, have I determined that I have a continuous function on a closed interval?
Now you have to check it within that interval.
Does this interval include any of these?
No.
Is 2 pi in here or not? Or is anything in there, right? So look, this is a positive interval, right? Pi over 4 is positive, 7 pi over 4. So 0 is not in there, right? The next possible problem would be 2 pi. Is 2 pi in there? No. How do you know?
Because it's just one more rotation. That was an 8.
Yeah, 7 pi over 4. If you look at 7 divided by 4, that's 1.75, right? 7 divided by 4 is 1.75. It's not quite 2 pi's, right? 7/4 is smaller than 2. So you know that this number is outside of the interval here. So continuous function, closed interval? Yes. But I couldn't assume that. And you can see there was some work involved in that, right? All right, so now that we know we can use the method, let's go ahead and take the derivative, which we did, and then I'm going to do my critical numbers. So first step, set the derivative equal to 0. So 1 minus 1/2 cosecant squared of 1/2 t, bless you, equals 0. Trig equation. How would you solve that? Anyone have any ideas? There's a couple of different things you could do here, but okay, so like you can move the 1 to the other side, or I can move this whole thing to the other side, right? And it would become positive. I think that's what I'm going to do, just because I want to work with positive numbers. So I just moved that to the other side, right? Now what? You can divide by half or multiply both sides by 2. Same thing, right? Either way. Okay, so I would get 2 is equal to cosecant squared. We're getting there. That. Anything else?
You take the inverse?
Not yet. Close. You could, but not
By
yet.
itself.
That squared is a problem. How about root both sides? You want to root both sides? What would happen if I take the square root on this side? Plus or minus, right? Root 2. On this side, cosecant of 1/2 t. We're getting there. I'm trying to solve this for t, right? What t would make this equation true? Now I heard inverse, right? The inverse, here's the problem. When you use the inverse function, you're going to automatically be restricting your domain, because the inverse function won't work unless we restrict the domain. So I do not advise breaking your calculator out at any point in time to do these problems, because you could potentially wipe out solutions that exist that way. Instead, let's go and do what we did every time we had trouble with trig functions. Try and get them in terms of sine and cosine. So how can I rewrite cosecant in terms of sine and cosine? Yeah, so this is the same as 1 over sine of 1/2 t, isn't it? All right.
Times both sides by sine.
I can multiply both sides now by sine of 1/2 t. If I multiply this left side by sine of 1/2 t, I'm going to have plus or minus root 2 sine of 1/2 t. And then the right side, what am I going to have? If I multiply this side by sine of 1/2 t? Just a 1. All right, we're getting there. Y'all see what I did? Divide by plus or minus root 2. I'm going to isolate sine. Still good? All right, now did we have the discussion about rationalizing numbers and how it's not that useful because we have calculators these days? This is a problem where rationalizing is going to help you, hopefully, recognize there's a very important number that's about to pop out here that you should recognize on the unit circle. You know, on the unit circle there were certain numbers you should just know, like 1/2 root 3 over 2, root 2 over 2. Right, those are some important numbers on the unit circle.
Yeah, except root 2 over 2.
Yeah, 1 over root 2, if we rationalize it, that means multiply the top and bottom here by root 2, right? Then it's going to become root 2 over 2. And then we'll add plus or minus, because that plus or minus is just going to follow us the rest of the way. Are there any questions? Plus or minus root 2 over 2.
That's just a ratio.
Yes. All right, so what I've done here is I've transformed this equation that had cosecant squared in it, and it all comes down to this. We're asking ourselves, when is sine, right? When is sine of something equal to plus or minus root 2? And so I go to my unit circle again. I'm going to draw my unit circle. Sine is which coordinate? The y coordinate. Where on the unit circle is the y coordinate root 2 over 2? Here? Is that the only place it's root 2 over 2?
On the other side.
Other side. What about negative root 2 over 2? And here. There are 4 different places where you could get plus or minus, right? Positive root 2 and negative root 2. That means I have 4 answers between 0 and 2 pi, right? Between 0 and 2 pi, I have 4 answers. How many answers do I have if I allow myself to open up to the whole interval? Infinitely many, right? And I'd have to find a general solution. I'm going to stick to the general solutions. I'm going to stick to it because it's more powerful that way, and I want to make sure everyone here knows how to get the general solution. So to get a general solution for this, what I do is I look at all of these, okay? I'm going to start at this one right here. Is there a way to go from this angle to this angle to this angle to this angle? Can I get from one to the other very easily?
Yeah,
Remember the last problem we had? We had these two. And I said, you know, what does it take to go from here over to this one? We just added pi and just keep adding pi to get around. How much do you have to add to jump from one of these to the next one? Pi over 2, right? 90 degrees. So if I start at this one, to get to the next answer, I just add pi over 2. To get the next one, add another pi over 2, pi over 2, pi over 2. But I could also go backwards, pi over 2, pi over 2, pi over 2. So to work towards my general answer, what I'm going to do is pick one of these. What angle is that? Pi over 4. And then from that, I need to add these little quarter rotations. So how do I say that? You just told me it was pi over 2, right? It's pi over 2, but I could have as many of those as I need. K times pi over 2. So if I replace k with 0, I get just that, which is this answer. If I replace k with 1, I'm going to have pi over 4 plus 1 quarter rotation. Understand this? All right, so this right here represents these 4 dots on the entire number line. You can have huge angles or small angles. This is every answer possible. And I want this, right, to be equal to that. So now I'm going to set this inside the argument equal to this. I just want a show of hands because I'm curious. For those of you who took pre-cal, does this look like does this look at all familiar? Like, were you kind of presented this in this sort of manner? Okay. No? Okay. Do you get it?
This actually makes much more sense when...
The way that, okay. I'm not trying to reteach this, but I understand that this is usually a gap for students. Like, this is something that, you know, people are like, what? Yeah, I never understood that in pre-cal. So I want to try and make sure you understand this. All right, I'm trying to solve for t, right? So multiply both sides by 2. If I multiply both sides by 2, right here, I get t equals pi over 2, right? That's what would happen if I multiply this by 2. They would reduce out, yes?
No, is that pi over 4, k times pi over 4?
Say again?
But pi over 2.
Right here?
Yeah.
It is pi over 2. Because what is a quarter rotation? Well,
90 degrees.
this is pi, right? So this should be pi over 2. Pi over 4 is this.
Okay.
This, look, the initial pi over 4 is where you're going to start. So I'm going to say, okay, start there, right? And then from there, add what? These things. Pi over 2s are 90 degrees. So from there, add 90, you'll be here. Add 90, you'll be here. Add 90, you'll be here. Get it? So distributing 2 here becomes t. 2 here, they reduce out, you get pi over 2. 2 here, you get what? 2's cancel. So you just get
Pi.
k pi or pi k, whichever you want. K pi. There it is. That's it. These are the places where what? Do you remember what we're doing? These are the values of t that will do what? Make what? 0. What 0? The derivative 0, right? We were trying to figure out where the derivative was 0. This is where it happens. Now, remember you have to look and figure out, do your answers live in here? So let's start cycling through some k's now. Let's start with thinking about this. The interval we're looking at are positive numbers, right? So I'm not ever going to plug a negative in for k. So let's start at 0. If I plug in 0 for k,